In the previous video, we had discussed the introduction to VSEPR theory, and in that we considered the examples of simple molecules which were having only the bond pairs of electrons. And in that case, the application of the VSEPR is pretty simple. We just have to think about the arrangement of the electron pairs surrounding the central atom such that there is minimum repulsion between the electron pairs. Now in this video, we are going to consider a little more complicated examples in which molecules have, in addition to the bond pairs of electrons, some lone pairs of electrons. And also we will discuss about the molecules which have multiple bonds. So to begin with, we'll consider the molecules having lone pairs of electrons. Now if you consider methane, then this is the example of a molecule which has only the bond pairs. There are 4 bond pairs of electrons, and as you know that the shape of the methane molecule is tetrahedral. It has 4 bond pairs, 1, 2, 3, 4 bond pairs. There are no lone pairs of electrons, and it's a pretty simple case where the bond angle is 109.5 degree. Now we go on to the second example, and that example is of ammonia, where the central atom is nitrogen. We must begin with the atomic number to understand the application, and atomic number is 7. We are concerned with the 5 electrons which are in the outer shell. Hydrogen, of course, has 1 electron. And now we will draw the electron dot diagram for ammonia, where you can see that nitrogen is surrounded by 4 pairs of electrons. See? 1, 2, 3, 4 pairs. So it's a case similar to methane, but it has 3 bond pairs. The electron pairs which are shared with the hydrogen, they are the bond pairs, and this one is the lone pair. So now how we are going to determine the shape of this molecule? So what we do is that we begin with the tetrahedral arrangement, because there are 4 pairs. Irrespective that whether there are lone pairs or bond pairs, there are 4 pairs. So we begin with the tetrahedral shape. So I have arranged the 4 electron pairs in the form of 4 bonds to be in the shape of a tetrahedron. 1, 2, 3, 4. But now one position, but it can be any one. It can be any 1 to anyone. Reason being that all these 4 positions are equivalent. We cannot distinguish this position from this position, because if we just rotate the molecule, the positions simply get interchanged, but you get the same shape. So these positions are equivalent, and it does not make any difference where we place the lone pair. So suppose we have placed the lone pair here. Now these are the 3 hydrogen atoms. Now when we consider the shape, we have to consider only the way the atoms are arranged without considering the position occupied by the lone pair. So keeping this in mind, the shape would be considered as pyramidal rather than tetrahedral, because you have to consider the shape formed by nitrogen and the 3 hydrogens. So this wedge line means the bond coming forward, and the wavy line means the bond going backward of the plane. So this becomes pyramidal, whereas when there were 4 bond pairs, the shape was tetrahedral. Now let us talk about the bond angle. So once again, the expected bond angle, because we have a tetrahedral arrangement, so the expected bond angle would again be 109.5 degree, a tetrahedral angle, but it won't be exactly 109.5 because of the presence of the lone pair of electrons. So the rule that we consider is, if you consider the order of repulsion, then the repulsion between a lone pair and another lone pair is greater than the repulsion between a lone pair and a bond pair, which is greater than the repulsion between a bond pair and a bond pair. Now there is a repulsion. This will be considered as the repulsion between the lone pair, and the bond pair, the lone pair and the bond pair. But the bond pair means this bond pair repulsion is less, and the reason is that the lone pair occupies greater volume because there is no positive charge which can balance this negative charge, whereas here the electron pair is attracted to the nucleus of the hydrogen, therefore it occupies less volume. So because of the greater volume, the repulsion is greater. A bond pair, there will be a minimum repulsion, so these bonds will go farther from the lone pair, and therefore the bond pairs will come closer together and the bond angle will get reduced and it becomes 107 degree. This bond angle becomes almost 107 degree. So you can say that due to one lone pair, the bond angle gets reduced by about 2.5 degrees. So 109.5 becomes 107. So that's now quite straightforward to understand. Now, if you now consider ammonia with boron trifluoride, now it appears that the shape could be similar because here also there is a central atom surrounded by three other atoms. Here also is the central atom surrounded by three other atoms. So we may consider that the shape of ammonia would be same as the shape of BF3, but it's not the case. As we already considered that ammonia is pyramidal in shape because we have to consider the arrangement of 4 electron pairs. But in BF3, we have to consider the arrangement of only 3 electron pairs. See, boron is surrounded by only 3 electron pairs. And the 3 electron pairs would arrange themselves in the form of a trigonal planar shape. So, the boron trifluoride is trigonal planar in shape, whereas ammonia is pyramidal in shape. Now let's consider another example in which once again the central atom, oxygen in this case, is surrounded by 4 pairs of electrons, but out of that 2 are bond pairs and 2 are lone pairs. So how do we understand that? We simply start with the atomic number of oxygen, the central atom, which is 8, and then there are 6 electrons in the outer shell. We arrange these 6 electrons, 2, 4, 5 and 6, and there are 2 hydrogen atoms which contribute their own single electron. So we have the water molecule, and this pair which is between hydrogen and oxygen is the bond pair, and the pair which is not being shared is the lone pair. So oxygen is surrounded by 4 electron pairs, out of which 2 are the bond pairs and 2 are the lone pairs. Now we will not consider only the bond pairs. For arrangement of the electron pairs, we will consider all the 4 electron pairs, and you know that the arrangement for the 4 electron pairs is tetrahedral. So we arrange initially the 4 electron pairs in the form of 4 covalent bonds, which might be formed in the form of a tetrahedron, but 2 of these positions will be occupied by the lone pairs. Once again, all the 4 positions are equivalent because it's in tetrahedron. All the 4 bonds are equivalent. It does not matter where we put the 2 lone pairs of electrons. They can put the 2 lone pairs of electrons anywhere, Now in this case, I have put the two electron pairs here and the two hydrogen atoms at the other two places. And now what would be the shape? Now once again, to consider the shape, we have to consider the shape formed by the atoms, not taking into consideration the lone pairs, because then there's no atom present over here. So the shape is formed by the atoms, not by the lone pairs. So you can see this is in the form of a V or a bent shape. So the water molecule is V-shaped, or if you can say it is V-shaped or bent. Now, for considering the bond angle, we will have to consider the influence of the lone pairs of electrons. Now, once again, using the same principle, that lone pair repulsion is greater than lone pair, which is greater than bond pair. So the bond pairs come closer together, going away from the lone pairs, and the bond angle gets further reduced to 104.5 degree. So in ammonia it was 107 degree. Now it is further reduced because there are two lone pairs and becomes 104.5 degree. So this is how we know that water molecule is V-shaped, and its physical and chemical properties point out to the fact that they can only be understood provided that water is a band-shaped molecule. It is not linear. Now if you compare it with BeF2, BeF2 is a linear molecule. We might consider that water should also be linear because it is one central atom surrounded by two other atoms. But the difference is in the number of pairs of electrons which surround the central atom. In beryllium, it is surrounded by two pairs, so they form a linear arrangement. In H2O, oxygen is surrounded by four pairs of electrons. They form a tetrahedral arrangement, but the atoms form a V shape. So this is how it's easy to understand the application of the VSEPR. Now let us consider what happens if it's a multiple bond. Like for example, if we consider carbon dioxide. So in carbon dioxide, carbon is surrounded by 4 electrons and oxygen is surrounded by 6 electrons, the outermost arrangement. So when we consider the electron dot arrangement for carbon dioxide, we get to know that there are two double bonds formed between the carbons and the oxygen. So two electron pairs are shared. So it forms a double bond like this. Now I have already drawn a linear shape. Now it is not a bent shape like in the case of water. It's not bent. Reason is that whenever there is a double bond, the two electron pairs, they are considered like a single electron. Why so? Because these four electrons or two electron pairs are fixed in space. They cannot go from this place. Like the two electron pairs are not independent. So they are considered as a single unit. This one electron pair cannot move to another position. So being fixed in space, it is considered as a single electron pair, and therefore we would consider carbon to be surrounded by two electron pairs rather than four electron pairs. And because of that, two electron pairs becomes now similar to beryllium difluoride, and the shape becomes linear, and the bond angles become 180 degrees. So now you have to keep in mind that a multiple bond is considered as a single electron pair because in the application of VSEPR, because those multiple electron pairs cannot move to different positions. They occupy the same position, so they are like a single bond. So keeping this in mind, it's easy to understand why carbon dioxide is linear in shape. So you will come across many other examples of molecules where it may be necessary to apply VSEPR and predict the shape and the bond angles. If you have understood the principles that I discussed in my two videos, it will not be difficult for you to apply the VSEPR and be able to predict the shape and the bond angles present in that molecule. Thank you very much.